Okay, so welcome to everybody. Today we have two seminars, and the first one is by Riccardo Zecchina, and I'm very happy Riccardo is here. So just let me tell you a few words on Riccardo's bio. He got the PhD in physics in 1993, working with Tullio Regge, but actually since that time already was working on neural networks. And then he moved to ICTP in Trieste. And at that time, well, we spent a lot of time working together already on application of statistical mechanics on problems from theoretical computer science. And then he moves to Politecnico Turin in 2007. And finally in Bocconi University in Milan, where he's now heading the Department of Computer Science in Bocconi. Riccardo spent most of his scientific life in performing statistical mechanics computation on problems coming from machine learning and theoretical computer science. And for this has been also awarded the Larson-Sager Prize together with Giorgio Parisi and Marc Mézard for the application of replica symmetry breaking theory to problems in optimization and theoretical computer science. And so I'm very happy you're here, and please.
So thank you very much. I'm really glad to be here, and I prepared a sort of tribute to Giorgio about essentially about his groundbreaking work, not only in physics but also in disciplines which are connected to statistical physics, and his contributions are actually playing a great role today. And so I think there's a lot of future also ahead of us and of these theories. So I will try to give a kind of an historical perspective, but also make links to what is happening today. And the approach will be pedagogical in some sense. I was thinking mainly about students, so I thought you might have not seen this kind of arguments, and so because they are kind of 15, 20 years old, and so I tried my best to do this. Now, essentially, for some reason, it's not. It doesn't move. Click on the slide. Okay. Thank you very much. So essentially, my argument is the following. One unique geometrical framework, which is related to replica symmetry breaking, captures the properties of very diverse problems in computer science, in machine learning, and in general, in non-convex optimization at large. So it's kind of interesting to observe that this scheme, this geometrical scheme in high dimensions, is actually relevant for many different fields. And depending on the field of application, you are interested in different aspects of replica symmetry breaking. So somehow there's a unifying framework that captures different ideas. So as we will see, just to make reference to this picture, which by the way is borrowed from a slide of Federico, when you're interested in optimization, somehow you want to find very narrow crystalline state in a very complex landscape. So somehow you are interested in the red dots in that picture, whereas when you do machine learning, you're interested more in finding very entropic regions. So somehow different aspects, in particular, that are related to subdominant contribution to the Gibbs measure of the associated physical problem, become relevant depending on the field of application. So somehow there's this unifying framework that explains a lot of different things. So just for historical reasons, let me just mention that, well, actually, this is the only autobiographic note that I want to make. I was a student in engineering in the late 80s, and I came across the papers of Giorgio about spin glasses, and I couldn't understand anything. It was the 5th year of engineering. And then I came across all these, the papers on optimization, on machine learning. And, you know, it was a kind of shock for me because I realized, well, there's something I don't know, something I should study more. And so I decided to switch from engineering to theoretical physics. I spent 1 year just studying physics and then applying for the PhD. I started a bit late, but it was worth. So in the 80s, Giorgio, Mark, and a lot of other researchers started to apply replica theory, so the theory developed for the SK model to optimization problems. So in the first part, I want to discuss this. And so, for instance, a very famous problem that was analyzed using replicas was the random matching problem, where you have essentially a bipartite graph, and you want to find assignments that minimize minimize the cost of the assignments. So you can imagine to have, you know, say, person and houses, and you want to find a matching between the left part and the right part of the graph, and the arrow indicates how much a certain person can afford for renting a house, or things like that. And so this is a very famous and fundamental problem in computer science. And so already in the 80s, they were able to make prediction about random realizations of these problems, and also make very interesting conjecture about finite size correction. And this has created a lot of interest in the math community, and there's been a lot of work. And so the seminar results of Giorgio, Mark, and other people were then proven to be exact about 20 years later. Using and to obtain this, it was necessary to develop new math. Another problem that they've analyzed was the traveling salesman problem. This is a very famous combinatorial optimization problem. It's an NP-complete problem. And again, they were able to give prediction about the behavior of this problem in high dimension when you draw random distances between points, and the issues and the challenge is to find a unique path that goes through all points exactly once that has a minimum total length. This is a very well-known problem in which, in the worst case, there's no known algorithm that can solve the problem in polynomial time. And they were able to make prediction about the random case. And, you know, this kind of ideas already raised the attention of the mathematician and computer science community, because when you have to deal with non-convex problems, you know, all of a sudden all the mathematical tools disappear. And so it was, for them, it was a great surprise to see that one could make predictions about these kind of problems. Okay. In the same period, the same techniques were applied to models of neural networks. In particular, the famous result about the Hopfield model was obtained in 82, I think. But not only that, there was a lot of work on feed-forward networks, in which essentially you take as energy function the number of errors that you make in classifying patterns, and then you want to, assuming that the patterns are random, you want to know, you want to address questions like what is the capacity of the network, how many memories can you store, how many patterns you're able to classify, and so on and so forth. So I will enter in more details later, but so these kind of things were already done in the 80s. These are some very famous papers, Replicas and Optimization by Mark and Giorgio, in 85. Then there was a paper here on replica analysis of the traveling salesman problem. I recommend the students to have a look at these papers. Then there's this other paper, the SK model, replica solution without replicas. This was a very important paper, in my opinion, because it paved the way for what is called nowadays the cavity method. And so they developed a method to obtain the same results as those obtained by replica theory, but without replicas. So it's a constructive approach in which you write set consistency equations for marginals. And somehow this was the precursor of what then became an algorithmic framework in, say, 15 years later. I also want to mention this paper, ultrametricity for physicists for personal reasons, because after having read all the papers by Giorgio on RSB, then I came across also this paper, which was very visionary by Miguel Virasoro, and this was the final step that made me decide that I had to change field. Okay, so the idea is that these are techniques to compute typical properties of problems that are characterized by a very highly non-convex energy landscape. Now, non-convex energy landscape in computer science means essentially NP-complete problems in the worst case. So problems for which there's no way of finding, no known way of finding an optimal solution in polynomial time. And so essentially the techniques developed in the context of disordered system are among the very few techniques that are able to make prediction, and in some cases to design algorithms for finding solutions to problems of this type. So what I'm going to show you in the first part of the talk is a discussion about the properties of, say, academic problem of this sort, but I also mention at least one application to concrete data. Okay. So later, after the 90s, say, there was a kind of a paradigmatic shift, at least this is how I perceived it. And the idea was, well, let's go beyond just making prediction about ensemble of problems. Let's try to address single problem instances, to turn all these analytical tools into actual algorithms. This was a very important step because it opened the way to use all the Spengler's theory for creating new algorithm and also gave new insight for the design of algorithm, which could maybe be based also on different principles. And what gave motivations for this kind of study is the fact that computer scientists in that period discovered phase transition in hard combinatorial problems. So that was a topic that was very fashionable at that time because as we will see, they discovered that depending on some control parameter, optimization problem could become very hard to solve at a certain point. And that was really a kind of phase transition. I mean, phase transition are not a new topic in discrete math. I mean, percolation is a very well-known example of a phase transition in a discrete problem. But here was really percolation in hard combinatorial problems. Sorry, phase transition in hard combinatorial problem, which was important because close to the phase boundary, what happened is that the algorithm turned out to behave in an exponential manner, which well, for the computer scientists was very important because they could finally study instances of problem, what kind of worst case instances of the problems. And so it was very important for them. So in that period, in the 90s, we all started to study this kind of problems. There was a very well-known paper by Scott Kirkpatrick and Bart Selman, in which they studied numerically a phase transition in a problem that I will describe in a few minutes. So what are these kind of problems? So I have digged some old slide. So essentially, what people studied were computer scientists were interested in were constraint satisfaction problems. So the idea is very simple. You have, let's say, n discrete variables, like Boolean variables, and then you have a certain number of constraints, like constraints among the Boolean variable. I think you can easily imagine what application of this. And so you can always construct, let me say, a cost function kind of energy, which simply counts how many constraints you are violating for a given assignment to the discrete variables. So these were the kind of problems that were of interest for computer scientists. I mean, in general, of course, this is a very general definition. Any optimization problem can be recast in this way. So clearly, if you have an algorithm for this, you have an algorithm for everything. So the issue was, well, I have a set of constraints, I have a total cost, and I want to know what is the minimum cost, possible cost for the problem at hand. Now, in computer science, in physics, we have similar problems, like say, when you want to study the ground state of a disordered system, more or less, it is the same kind of problem. You want to satisfy all the constraints given by the interaction energy of the bonds in a spin model, for instance. And you're interested in knowing which are the property of the ground state of the system. So at zero temperature, where does the system relax? In computer science and in physics, we are interested in, say, for instance, in the average properties over an ensemble of problems. In computer science, there is a different approach. You really want to be able to solve a single instance of a given instance of the problem. So you have an algorithmic perspective. So typically, this, you might be, it's a useful thing for those of you who have not seen it, but normally these kind of problems are represented on graphs, random graphs, which are called factor graphs, where the squares represent the interaction and the circle represents the variable. So when you have a square with three circles connected to it, it means that you have a constraint that involves three variables. Okay, like I have a dinner party and I want to invite X and Y, but not Z. And so that would be a Boolean constraint on the variables. Okay, so in general, you can represent your combinatorial problem as defined over this graph, which is called factor graph. This is a name borrowed from coding theory, which also has a lot of connection with the replica theory. And the idea is that over this graph, you want to find a configuration of the circles such that all the squares are satisfied simultaneously. Okay, so this was the problem that we were interested in. I mean, the community was interested in, and it's called the satisfiability problem. This is a very, very famous problem in computer science. So the problem can be stated as follows. So you have n variables, Boolean variables, xi, which can take the value 0 or 1, so false or true. And then you have a Boolean formula, which is written as the conjunction of many clauses. You see, you have x1 or x7, not x7 or x20, and another clause and another clause. So each term in the bracket is called the clause, and it's composed by taking the or of a certain number of Boolean variables, and then you take the and of all these clauses. Now, since given the property of the and, which is essentially a product, in order to have this expression equal to 1, what you need to have is that all the factors need to be equal to 1. So trying to find an assignment of a Boolean variable such that the overall function evaluates to true is totally equivalent to say, to pretend to find an assignment that satisfies all the constraints simultaneously. So just to say that this is a very, very fundamental problem. And in fact, this is one of the first problems proven to be NP complete by Cook in 71. So essentially, what you can prove is that any problem for which a solution can be checked in polynomial time can be mapped onto a SAT expression. And therefore, if you have an algorithm for SAT, you can solve all the problems that are so-called NP, namely non-deterministic polynomials. So any combinatorial problem for which a solution can be checked in polynomial time can be reduced to SAT. Therefore, SAT is, let me say in a physical language, it's more kind of universal. So if you can solve that, you can solve all the rest. This is just just to say that this is a very fundamental problem. Now, this kind of classification of problems is what is called worst case classification. In fact, we are not interested in that. We are interested in actually the typical behavior of this kind of problems. Let me mention, just for the sake of completeness, that the connection between complexity theory and physical models is actually very deep, because even just computing the partition function of an arbitrary spin model is actually an NP-hard problem. So there are many theorems, but let me mention this one. So there can be no approximation algorithm for the easy spin glass unless P is equal NP. What does this mean? It means that there's no way of computing the partition function of a spin glass model unless all the complexity classes collapse to the class P. So in other words, if you could come up with an algorithm for computing Z, you could solve any combinatorial problem you could think of. Okay, so this is a very fundamental problem. Now, all this classification is based on the worst case analysis. Now, computer scientists are interested also in the typical case. So what happens with high probability? The problem is when you generate problems. The problem is that it's much more difficult to create a theory for typical case complexity, for average case complexity, because problems come with attached a probability distribution. And so when you transform one problem onto another problem, you have also to specify how the ensemble changes, and so things become very, very complicated. In any case, so what happened in the 90s is that computer scientists started to study random formulas, random satisfiability problems. And what they have noticed is that as you increase the number of constraints to the number of variables, all of a sudden, the problem becomes unsatisfiable without high probability. So if alpha is small, so alpha is the ratio between the number of constraints to the number of variables. So if alpha is small, namely it is under constraint, then it's easy to find a solution. You have a lot of variables and few constraints, you can find a solution. If alpha is very large, so you have more constraint than variables, so it's over constrained the problem, there are no solutions, and in between there is a phase transition. Now, so this is more or less the behavior. So as you increase the number of variables, the number of constraints with respect to the number of variables, at a certain point, you have a threshold phenomena, and above a certain critical value, when you generate a formula for n large, with high probability, you generate a formula that has no solution. So there's no way of solving the constraint satisfaction problem. Now, what made the thing really interesting for the community was the fact that it was an experimental observation, is that just before the transition, there is a wide region in which algorithms display an exponential behavior. So all known algorithms. So there is a region where, so if you generate a formula with a ratio of constraints to variable, which is below but close to the critical value, then there you create problems that are hard to solve. So for computer scientists, this was a kind of a magic result, because all of a sudden you have a generator of hard distances. So you want to know why they become interested and what's happening. That was a very fundamental problem for them. Okay, and so this is where the contribution of statistical physics started in this specific problem. I mean, in the study of this kind of phase transition. And the question we wanted to answer at that time was, what makes this basic problem hard to solve? As I said, computer scientists were interested in random instances for several reasons. One was the onset of exponential regime in algorithms, so why they become hard to solve, which are the geometrical properties, the structural property of these hard problems. In order to understand this behavior, new mathematical tools had to be invented because they had no way of analyzing these kind of problems, whereas using for instance, Giorgio's framework was actually possible to say a lot of things about this kind of problems. So it was it opened a lot of doors. And also there are a lot of applications of this kind of theory in coding and cryptography. Because if you are able to prove that something is hard to solve, this is fundamental for cryptography. Cryptography is about proving that something is hard to solve, and then you use the property of hardness to build a cryptographic system. I don't have time to discuss this, but this was more or less the philosophy behind it. So what happened around the year late 90s, 2000s, is that we as a community started to study random constraint satisfaction problems. So you have to imagine that when you represent these problems on a graph, they become random graphs, random factor graphs, which are of the Erdős-Rényi type, namely the degree of each node, as a Poisson distribution. So it's a finite connectivity graph. And so the interest shifted a little bit in this field from fully connected model that characterized, say, Spinger's theory in the 80s to a mean field theory over more sophisticated structure, namely finite connectivity random graphs, for which you have a notion of distance, because you can define the distance between 2 points on a graph, whereas on a fully connected graph, the distance is always one, say. Here, the distance is defined by the shortest path between 2 nodes. So, so there was a lot of interest in trying to generalize all the techniques of developed for the SK model to this kind of finite connectivity system. So there was a lot of work by Remy Monasson on the Replica Method. And then in the year 2001, Mark and Giorgio came up with a very important paper in which they showed how to generalize the cavity method to this kind of graphs, including replica symmetry breaking effects. So somehow they devised a technique to compute typical properties of problems defined on this kind of structure without using replicas, but by using self-consistency equations for marginals of the variable. And this, had an algorithmic flavor that was really important. And this is the paper we are supposed to celebrate today. And so this was a paper in which the kind of technique developed in this paper, but also in the other papers, there were a lot of hybridization, say. So in this paper, what we did was actually to study and analyze the random satisfiability problem and compute the threshold behavior. But not only that, while doing this work, we realized that if you look at the cavity equation, so this alternative technique to replicas, in the case of random systems, the hypotheses underlying the cavity method do not depend on the fact that you take average over the disorder. And therefore, they could be, in the larger limit, they could be executed over single problem instances, taking into account all these complicated structure of ground states that I mentioned at the beginning. So it was possible to not only to predict the typical behavior of formula, but it was also possible to design an algorithm based on these analytical techniques that was able to solve these problems. And this, probably, I think it's fair to say, that came as a real surprise to the entire computer science community, because at the beginning they were very skeptical about the tools of statistical physics, because they used to be non-rigorous at that time. Now most of the results have been, many results have been proven to be exact rigorously. So there was a kind of skeptical approach to the results that we as a community presented to the computer science community. But after displaying an algorithm that can actually solve the problem, then the attitude changed completely. So the idea, what happens in this kind of problem, I will be very qualitative, is that as you approach the phase boundary, so as I said, if you have few clauses and a lot of variables, the problem is easy to solve. And all the solutions that are, you have a discrete variable, so they are on a hypercube, they are all connected. So the space of solution creates a cluster or a connected cluster, and this green ball on the left. As you approach the phase transition point, then all of a sudden this connected cluster solution breaks into an exponential number of smaller clusters. And this is replica symmetry breaking. Okay, so this way of breaking the symmetry of disordered system was a great surprise for the computer science community. Imagine you have, if you are a computer scientist, you know nothing about symmetry breaking, and all of a sudden, in the most fundamental problem of your field, somebody comes and tells you, well, this is how the problem becomes hard. And not only tells you that, it also gives you an algorithm to exploit this. So it was really kind of interesting. And in the region below the critical point, where you have this clustering of solution into an exponential number of clusters, of course, above, this is at zero energy. So this is for the ground state. At higher energy, you have a lot of metastable states. And so, this is the reason why, for instance, algorithms like Markov chains, like simulated annealing, that try to minimize the energy, in particular following the tail balance principle, they will get stuck at a certain point. So there are many reasons. Now, I will mention this later. So, but this was more or less the scenario, which was really fascinating at that time. So these are the two figures in the paper. So on the right, you have the evaluation of the critical value, which is around 4.26. It's a totally irrelevant numerical value, but it was something that being able to compute the number was a witness of the fact that one should control. Sorry. Okay, sorry again. So the idea of, okay, there were a lot of, there was a lot of discussion, but overall, that's the year where the relationship between community changed quite substantially. So in a nutshell, the idea behind this, the cavity method, the replica symmetry broken cavity method that we used to call at that time survey propagation, is essentially that you have to write for each cluster. So let's say for each ergodic component of the phase space, in each ergodic component, you have a marginal describing the probability distribution of the variable inside that component. And since you have many different components, you have to describe how these marginals fluctuate when you go from one cluster to another cluster. So the overall setup was to write equation for probability distribution of marginals, so probability distribution of probability distributions. That was the key idea. And this is, so it's a, let me say, a higher level of mean field equation. It's a mean field equation in a space of functions. Okay. And so under certain hypotheses, which are those that make the replica method valid, this equation may lead to exact results. So, and they allow to compute several interesting quantities. They can allow you to compute which is the typical entropy of one of these clusters, which is the number of cluster of a given entropy, what is called the complexity. So you can have access to a lot of information, or what is the probability if you pick up a cluster at random that a certain variable has a certain field acting on it. So you can use this really to make predictions about the behavior of single variables inside a very complicated system. And this was, I think, really really interesting. In particular, if you think that this equation can be run and implemented over single problem instances. So you give me a random SAT formula made of 10 million variables. I run this equation, which converge in linear time or n log n. And then I'm going to tell you, well, if you freeze that variable, you will observe a certain change in entropy, a certain change in the property of the system. You check it and it works. So it's really something that allows to make predictions, about single problem instances. And so this really, to me, it was a very exciting moment, because it's really the idea of bringing all the theory developed by Giorgio to to enlarge the range of application of the theory. Okay, so go beyond the average prediction about average properties, but deal with single instances. Then some years later, there was a great work by Federico and Karzakala, Montanari, Semerjan, and Lenka Zeborova, in which they gave the precise picture of the structure of clusters in this problem and in similar problems. Because in our original work, we were only interested in the number of clusters in respective of the internal entropy. We just wanted to know how many clusters were generated. So we used, say, an approximation, which was enough for us to compute the critical value and to design an algorithm, but was not complete. And so they analyzed the complete picture. And so this is more or less what happens as you increase the number of density of constraints in a hard optimization problem. So you start with, at low ratio of constraints variable, where you have a giant cluster of connected solutions. The problem is easy to solve, and it's easy to go from one solution to another solution just by local moves. Then the cluster starts to break into an exponential number of smaller clusters, and this is called the dynamical RSB transition. And then there's another transition point where the number of clusters becomes sub-exponential, and this is called the condensation threshold. And so you're left in a phase where you do still have solution, but it distributed in few clusters, and then you have all the solution disappear. So this is, I'm not going into details, but this is more or less the scenario that came up. Now, 10 years later, so more or less 15 years later, the first solution of this problem was proposed. Alan Sly, Jean Ding, 97 came up with a rigorous proof of the exactness of the prediction, at least for k large enough. And so somehow, I'm the only one. I'm the only one to, or is it a common problem? Okay. Anyhow, so maybe I can try to do this. Okay. And so, you know, there was a lot of work by mathematicians, because for them it was really a big novelty. And so they were able to put on rigorous grounds all these results. Now, let me just say a few words about what is called the survey propagation algorithm. So the idea is that you take the functional equation that I briefly mentioned before, and you take you project this equation into somehow simpler quantities, which means essentially that you only look to the contribution of the local fields which do not scale with the temperature. So you're just essentially ask yourself whether a variable is frozen or not in a certain direction, or you say that it's irrelevant. This you can show it's enough to compute the number of clusters and the bias of the variable. You cannot have access to other quantities like the entropy inside the cluster, but doesn't matter. This quantity, this projection of the equation onto this simpler object that are called warnings, that we used to call warnings, that correspond to extend the Boolean algebra from 0, 1 to 0, 1 star, where star means the variable is in a don't care state. Then we were able to write the equation in this particular setting, and this turned out to be a very efficient algorithm. So essentially the idea is that the algorithm works as follows. You iterate the equations, and then once you converge, you're able to compute for each variable what is called the bias of the variable. So what is the probability that you pick up a cluster at random and you find a variable frozen in a certain direction? Once you have this information, what you can do is to say choose the variable that has the highest bias, fix the variable in that direction, and then rerun the system of equations in an iterative manner. This turned out to be a super fast algorithm for solving satisfiability problems. And so in the picture on the right, you see it's the log of the number of clusters depending on the energy of the cluster. And as you proceed in this decimation process, you see that the number of clusters shrinks, and then at the end you're left with just few variables that are not fixed, that are totally paramagnetic, that are easy to fix by any greedy algorithm. Okay, so this was a very, very powerful algorithm that was able to solve. So here on the left, you see there's f. F is the fraction of variable you fix at each step of the decimation. And then in the columns, you see you have alpha equal 4, 21, 22, 23, 24. So values very close to the phase boundary. And on the upper row, you have the size of the problem. So if you just look at the last column, you see that very close to the boundary, if the fraction of variable that you fix at each step is sufficiently small, you solve, say, 100% of the samples. So this was very, very surprising. Then there were other versions of this algorithm. There was one that Giorgio developed, which was called the backtracking, that was behaving even better than this. And then we were further developed more recently, not of this algorithm, but still based on replica theory, algorithm for sampling from the SK model. I'm just mentioning this result to say that, again, there's this algorithmic flavor of replica theory. Now, I don't know if you know this, but in the famous book, The Art of Computer Programming, Volume 4 by Donald Knuth, there is a chapter on survey propagation in which, 5 pages, in which he analyzes, describes, and implements the algorithm. And, it's just enough to look at the last sentence. Success with algorithm S, which is survey propagation, isn't guaranteed. Totally true. These equations are not, do not converge always. But hey, when it works, it's sometimes the only known way to solve particularly tough problems. Now, coming from Donald Knuth, so this is kind of the Bible of computer science. It's kind of, I think, a nice story. So now let me show you this piece of, this is just 1 minute of a talk by Christos Papadopoulos gave in 2018 at the Simons Institute. Now, you have to imagine that Christos is a reference figure in theoretical computer science. He was one of the researchers who built the complexity theory. And when we met and you were there in 99, it was really opposed to our approach to hard optimization. It was against any interdisciplinary contamination and so on. And this is what he said.
That phase transitions are tantamount, coterminous, equivalent. In other words, what phase transitions really mean is that one particular randomized algorithm converges exponentially faster. Okay, and this was sort of, an incredible insight that changed the field dramatically. In the following sense, that's in some sense the greatest success story. Now there is a new field, and you have great algorithms published by physicists. Okay, so and theorems in physics proved by computer science. So you have this very active and harmonious sort of reaction, interactions.
Okay, so I think it's kind of amazing. So after, say, 20 years of work, finally there is a community. So I agree with Chris. It was a success story that all emerged from the work of Giorgio in the 80s. And so nowadays there's a really, more in the US than in Europe probably, there's a lot of interest in all these techniques. Now, as I told you that, so as far as optimization problems is concerned, the issue was to be able to find the solution of this constraint satisfaction problem. I just mentioned satisfiability, but I could mention a lot of other problems. And the challenge is when you're very close to the phase boundary, you have these few clusters of solution, you want to find the very last ones. So these are kind of crystalline solutions inside a very complex landscape. Now, this is not always, for other type of problem, this is not the real challenge. But before I just want to mention one application. There are many applications, but this I think was kind of successful. And one application of this algorithm was in the prediction of protein contacts from sequences. So when you have a family of proteins, they evolve, right? And so for a given structure, you have many sequences that give rise to the same structures, even though the sequences are different. So one can study the correlated mutation in these sequences and try to infer from correlated mutations where the long-range contacts are in the protein. And this is fundamental for predicting protein folding. By the way, AlphaFold uses this information, this very famous algorithm to predict protein structure. And so the very first application of this problem the first algorithm to predict contact was actually done using the kind of message passing algorithm developed in the context of the satisfiability problem in a simplified setting. But this was the case because, I mean, it was Martin Weick, the first author in this paper, who was in our group in Turin. And so he went to visit Terry Waugh and they applied this technique. So I think it was, and then, this gave rise to a lot of new insights and very important results in biology. So I think this is a very concrete example of an application. As I said, so let me say that roughly speaking, what we've done is mention the fact that for hard combinatorial problem, the challenge is to find rare solutions that are very tiny in a complex landscape. This is what combinatorial optimization is about. And also it's what source coding is about. I don't have time to discuss this, but there's an entire field of communication theory in which, again, the problem is finding solutions that are very narrow in a very complex landscape. Now, in machine learning, let's come to our days. In machine learning, the challenge is different. Again, we have a very complex landscape, but the challenge is I want to find ground states that are as entropic as possible. So it's, again, it's the same setup, but with an opposite scope. But again, it's described by the same kind of tools and ideas. So as you know, the research in machine learning was, in neural network had a peak around, again, 80s and 90s. And I think Giorgio had a big responsibility on this, because essentially in applying the technique that were developed for the SK model to neural network, I mean, the possibility of applying this technique created a lot of interest in the community. And so there was a lot of work in the 90s, but then there was a kind of a lack of success in say, applications or predictions. And so somehow there was a winter period in statistical physics of this kind of system, and which now is again is changing, because now we are again interested in this kind of system, because we are witnessing a real revolution in machine learning. And I think we have a lot to say about it, because these are huge systems with very interesting properties that could be addressed using the techniques that we are discussing. So again, training a neural network is, just like satisfiability, is in principle a very hard computational problem. These are highly nonlinear systems. The problem one has to solve when doing learning is highly non-convex. I will show it in a minute. However, there are some surprising results that need to be understood. One is that for some reasons, algorithms that are they've been designed for convex problem turn out to work very well also for these highly non-convex problems, provided you add some twists and you somehow perturb the system and keep it, say, out from reaching an equilibrium distribution, which is just what you would get by letting equilibrate the system. So let me say, the simple algorithms like gradient-based algorithm can be modified to be successful in this kind of setting, and this has to be understood. This algorithm leads to solutions that have very good generalization properties, and this is not at all obvious, because these are huge systems that in principle could overfit. Now, in the 90s, when we used to study this problem, we were actually avoiding overfitting. We were trying to use algorithms that were converging to the Gibbs measures. And these are not things that are going on today. So somehow we were biased to look into this problem in, let me say, in the wrong manner. Not because of the tools, but it's really a priori a conceptual problem that we had. So very briefly, the kind of system we are interested in are essentially multi-layer neural networks of this type. Again, you give an input, you read the output, and you want the output to be a desired output. And this desired output is, given by your training set. So you have data like pictures in the input, and in output you have labels, like say you have a picture that contains a bottle. So the node corresponding to the label bottle should light up when you present the bottle in the input, things like this. So associations, right? So this kind of neural networks, each node implements a nonlinear transformation, and this is why they're called neural network, and and receives inputs from neurons in the layer on the left, and each link has a weight, and these weights are the parameters that we have to choose. You have to choose in order to have the whole system to make the overall system implement the desired input-output association. So the learning problem consists in find the connection weights such that on a given training set, this network is implementing a desired function. Now this, as you can imagine, this is a composite nonlinear function, very, very highly nonlinear, universal. Any function can be written in this form. So training this system, namely minimizing the number of errors that this function makes on a given training set, it's a highly non-convex problem. Just like, say, satisfiability or whatever. In principle, it's an unsolvable problem. In practice, it turns out that it's easier than what we expected. It's easier than what we expected, in particular, because we can over-parameterize this system. So we can take systems that are really large, and so somehow in this large space, it's easier to find the ground state, even though the problem is non-convex, and so to minimize the number of errors, and still the solution we find generalize pretty well. So there's this thing, this ingredient was missing in the 90s. We were studying a system with the minimum number of parameters. Here we consider systems that are highly over-parameterized. I mean, you know very well, GPT-3 has 200 billion parameters. So it's really a huge system, right? So the idea is, again, what I was mentioning is that there was a statistical mechanics approach to this kind of problem. The idea is that you take the number of errors as an energy function, and you want to find the configuration of the W's that minimize this number of errors. Now, the point is that what is relevant for algorithms are not the typical states, so the dominant states, those that are, say, mostly frequent in the ground states of the associated problem. The relevant ones are those that are particularly entropic. And so in order to do this, so somehow, you know, the Gibbs measure at low temperature, so the minimum cost configuration of the weights, those that corresponds to good learning, can be thought of as these green circles. So they can be very, their number can be very large, can be exponentially large. But what is of interest for algorithm are kind of rare configurations that have a high internal entropy. So somehow, given the entire description of the replica symmetry breaking structure of these problems in the case of random patterns, you want to find not the typical states, those that dominate the Gibbs measure, but you might want to find other states that are subdominant but have a very high internal entropy. This for various reasons. One is that they attract greedy algorithms. Second, that they generalize well. Of course, this has to be proven. And so the idea is that so in order to understand if this was the case, we analyzed the simplest possible non-convex neural network problem, having this in mind. And so what we did, just because I think I don't have much time. So as I said, so what we did is the following. First of all, we looked at for this kind of network, in the case of binary weights, just for simplicity, we look at the property of the space of solutions, just like we did in satisfiability. Now, for this kind of problem, what you find is that the typical solutions are just like a golf course. You have a lot of point-like solutions that are far apart. And in fact, if you run a simulating annealing on this kind of on this simple network with binary weights, you never find zero error configuration. You are unable to learn. You get trapped. And as n increases, you get stuck at higher energy. And there's no way of minimizing the energy if you use a Monte Carlo approach in which you try to satisfy detail balance to minimize the number of errors. And the reason is that it's really a glass in which you have a glassy states in which you get trapped. So a perfect spin glass. Now, the problem is that we had numerical evidence that in fact learning is possible, but you have to abandon the idea of satisfying detail balance and you have to look for other type of solution, which might be subdominant in the Gibbs distribution, in the Gibbs measure. Okay, and so in order to understand this, we decided to look at say the replica symmetry breaking framework with a different tool, which essentially it's a large deviation 1 RSB technique. What this means is that instead of looking to solution, what we did is we said, okay, let's take an hyperspheres of radius d, some macroscopic radius, and let's count how many solutions you have in this hypersphere. And then let's move this hypersphere around. So the question is, do regions exist that might be rare, but do they exist? Can you find regions where you have a particularly high density of solution, even though they are subdominant? So this was the challenge. Technically speaking, this is just like doing a 1 RSB calculation where you do not optimize over Q1. Just for those of you who are experts, you just use it as a lens to move around. So maybe, yeah, so this is you define a length of radius d, and you use it to explore the landscape, okay, analytically. So you can do this, and indeed what you find in this network that have a golf course distribution of solutions, that there exist in this golf course, there exist lakes that are very dense in solution, and those are the lakes that are found by algorithms. So you have these rare regions that can be accessed by algorithm, and they also have, you can compute generalization performance, and they have very good generalization performance. So why they have good generalization performance? Because you can show that these lakes contain solutions that have a very high margin. So they are very robust to perturbation of the parameters. So it's exactly what you want to generalize well. You want to find not only a configuration of the weights such that the function implements the correct input-output association, but you also want this function to be particularly robust either to noise in the input or noise on the parameters. That's what is, generalization is about. Okay, so this was actually the result that we found, and I think I don't have much time, so I will skip. I just want to mention that there are some theorems, recent theorems, that show that if you have a clustered, in this kind of systems, if you have a cluster configuration, so you have just a golf course and you do not have these dense regions of solutions, then it's actually impossible for stable algorithms to find solutions. Essentially, there's no way a stable algorithm can find stable means an algorithm that is smooth for perturbation in the input, roughly speaking, like would that can find solutions if the solutions are well separated in cluster. Whereas if you have these regions that are dense in solution and very wide, then it becomes possible. Okay. Now I just want to mention that again, just as happened with the survey propagation algorithm, also for this large deviation technique, one can derive algorithm from the statistical mechanics formalism. I'm not going to spend time on this, but it is possible. They work very well. And in particular, entropy SGD and sharpness-aware minimization are two of these type of algorithms that are really successful and widely used in the community of machine learning. They don't know the results come from here, or they know it, but they don't care. But it doesn't matter. It's fine. So, so now very briefly to conclude, I just want to mention two things. One is that one can also ask what happens in the case of over-parameterized systems. So, and the idea is that if you take a system there's one important result in machine learning. So suppose you have a system that has more parameters than data. You normally think that you're going to overfit, right? So if you want to fit points with a high degree polynomial, you start to oscillate and your prediction will be very bad, right? Well, this is not the case in the sense that if you go to a highly overparameterized system, essentially what happens is that you're going to fit points in a way which is stable. So in a sense, the idea is the following. So if you have points, say like this, and you want to fit them, if you use a straight line, you're going to make this kind of prediction, which is good. If you quadratic fit, you're going to do something like this. If you have a polynomial of degree 50, you're starting to do things like this, and which means that as soon as you move, your prediction will be very bad. Now, if you use a highly overparameterized system to make this prediction, the kind of fitting that you do just intuitively will be something like this. So you see, you use the nonlinear, the high degree at your disposal to actually create this very non-analytic behavior of the curve, but overall the curve is stable and makes very good predictions. What? Did I say it's intuitive? No, it's not intuitive, not at all. Oh, no, the picture is intuitive. I mean, when I say it gives an intuition, why it is so, it's one of the, I think, most very innovative results about modern machine learning, right? And so this can be for linear problems with huge kernels. Okay, this is technicality, can be analyzed, but for non-convex problem, this is totally, this is very interesting and new. So somehow in the 90s, when we were studying neural network, we always said, okay, let's keep the number of parameters small to avoid this kind of oscillation. But in fact, this was not necessary. Now, the classical statistical learning theory predicts for the generalization error the U-shaped curve that you see there above. So when you increase the complexity, so the number of parameters of the model, you start to overfit. But in reality, this doesn't happen. So for instance, this is a numerical example, a very famous paper in which here on the horizontal axis, you have the size of the network, and the black curve is the training error, and the red and blue curves are the generalization error. And you see that there's no sign of overfitting as you increase the size of the system. So essentially, the idea is that one can study this problem, for instance, using what is called the random feature model, which is a kind of a support vector machine. It's not, again, not very important, but you can design a model in which you can control how many parameters you have in your model irrespectively of the number of patterns. So you can overparameterize at will your network. And if you do this, let me go directly to the result. What you find is that, okay, in this diagram, you have, if you move from top to down, you essentially increase the degree of overparameterization. So as you go from top to down, at a certain point, you encounter a first. So if you are above, very high in the picture, you have low overparameterization, which means you do not have enough parameters to fit the data. Then you encounter a first line where you start to be able, in principle, to fit the data, but these wide minima are absent. And then you have a second transition point where these wide minima start to appear in the large deviation study of the problem. And it's only after the second line where algorithms start to work, and then you can also compute the generalization error, and things seem to work nicely. So just to say that if you look at if you can study the phase diagram of overparameterized model by using this large deviation technique of replica symmetry breaking scenario, then you can understand this kind of phenomena, at least in certain models. There's also experimental evidence. And then I want to conclude, since I'm very late, I apologize, with another paper of Giorgio, which I find very beautiful. I again suggest students to have a look to this paper, which is asymmetric neural network and the process of learning. I remember another paper by Giorgio, the title was something, neural network that learns to forget, or something like that. There's always this sense of humor that I always found amazing. But so the idea here is, again, this is related to how to use replica theory in understanding modern problems. So this is a problem of studying an attractor neural network with asymmetric couplings, which is the realistic version, let me say, of the Hopfield model. Everybody knows about the Hopfield model. I mean, the Hopfield model is a model of associative memory where you, given a certain learning rule, you can essentially design this system in such a way that the minima of the free energy are close to certain configurations that are the memories stored in the system. So essentially, you can store pattern as minima of the free energy. The problem is that that system has symmetric couplings, which is totally unrealistic. One of the many problems. So what we would really like to do is to study this kind of networks. And nowadays, there's a lot of interest in this kind of problem. So the whole community is going back to this kind of results. And Giorgio here was proposing some ideas of how to train this system in a successful way. And so what I just want to mention is that also for this system, the replica approach turns out to be, I think, particularly insightful. What happens here is that, so essentially the kind of problem we want to study for this system, so this is an asymmetric neural network that has some update dynamics, which could be, for instance, the one written there. So SI at time t+1 is just given by the sign of the local field. So this would be one possible dynamics. And you would like to ask, how many fixed points does this network have? So because the fixed point are the memories, right? And so one can in the totally asymmetric case, in which there's no correlation between Jij and Jji, so the couplings between two variables. So essentially, in the optimization language that I introduced before, you have a number of constraints that you want to satisfy that are these fixed point constraints, which are, so the number of fixed points, the constraints are the sum over I, so each node has to be in a fixed point. So you have a sum over I from 1 to n, which is the number of neurons in this network. And then that function over there is equal to 0 if the fixed point condition is satisfied, or is greater than 0 if it is not satisfied. So you want to minimize that number, that total cost. In other words, compute how many configurations you have of cost 0, so how many fixed points you have. And now, if you do this for this kind of system, we have not published this result, but it's nice to know that one can compute the number of fixed points exactly. Here, there's also self-coupling in the system. This, you see, the JD SI at time t, so you have a self-coupling, otherwise there's no solution at all. But as a function of this self-coupling, one can compute the total number of fixed points, and it's very interesting, and you can prove that the first moment is exact, so it's a very nice calculation, and okay, this is a nice result. But the problem is that this network is totally chaotic. And so there's a lot of work. You have these fixed points, but all these fixed points are unstable. So there's a lot of work about chaos in asymmetric neural networks. Now, I've never understood really how one can use chaos to perform computation in associative memories. So my question was, what we started to think about is, are there other states which are that are not dominant, maybe are subdominant, but that are actually stable? And so we applied the technique that I described before. So we looked at the symmetry broken scenario with this large deviation perspective. And what we found is that indeed, as you change the self-coupling, for very small self-coupling, this network, beside the fixed points that are unstable, has some stable fixed points that are very narrow and unreachable, given the theorem that I mentioned to you before. These are very isolated. So this is a perfect code in a sense. So it has very few fixed points, as a very, large number of narrow fixed points that are stable. However, they are not reachable. There's no way of finding them. But then there is a very interesting phase, which we call the liquid phase, in which this very tiny cluster become connected together. And so you have a very wide regions of fixed points that are connected, that are stable, and so that could be used to perform computation. And one can just apply an external field and make the system converge to a fixed point which is close to an external signal, and so on and so forth. So just to say that also in the context of attractor systems, again, the replica symmetry breaking scenario has not ended at all to give new insights, because while it is true that most of our community is studying chaos in this system, we actually should consider the fact that there are these states that are extremely interesting. So just to conclude, I tried to give you at least 3 examples. One was combinatorial optimization of hard problems. The other is the phase space of non-convex neural network, and the other are the dynamics, the fixed point dynamics of attractor networks, in which we have a single kind of geometrical framework that gives different insights if looked from different perspectives. And so I really want to thank Giorgio for all this. Thank you.
Thanks, Riccardo. Any question, comments?
No, io volevo solo ricordare, cosa che Riccardo non ha detto, che il lavoro, quello che aveva citato con Mezzara su Revisiting e Bethe Lattice, the Bethe Lattice Model rivisitato, era nato proprio dopo una conversazione che avevo avuto con Riccardo a Trieste, che mi aveva suggerito di studiare questi modelli diluiti. Io gli ho detto che non era possibile, ma cercando di convincerlo che non era possibile, ho scoperto che invece lo era.
No question. I just want to ask you a general question. So, about the interaction between physics and theoretical computer science. So, how do you see the situation now, after 20 years of attempts of doing something together?
I know. Okay. So there is a lot of activity. So what theoretical computer science would love to do is a theory of typical case complexity. So because the theory that they built is a worst case analysis. So you essentially say, well, these problems are equivalent under a worst case hypothesis. But this is not, as we know very well, what would be more interesting, in particular in light of modern artificial intelligence, is to say, which are the hardness properties of problems when linked to a given probability distribution that is used to generate these problems or questions like this. So there is work in this direction, and there's a great interest. The problem is that it's extremely, extremely difficult, because when you try to map one problem onto the other, you have to map the probability distribution. You want to impose some stability conditions. It's a nightmare. There are very few theoretical computer scientists that are brave enough to even think about this, but it's certainly what's in their mind. And so at the moment, there's a lot of interest in trying to think about hardness property, again, cryptography, and all this kind of thing. And then I think that in AI, there's the need of theoretical physics, absolutely, because you have this huge system and that cannot be analyzed, are difficult to simulate. So we need non-trivial models, and we need to analyze them. Keeping in mind that there's a lot of numerical evidence that we should incorporate. So it's a very, very challenging field, but it's certainly super active.
Okay, thanks. There are no more questions or comments. We thank again Riccardo.